that there were some extra conditions when we discussed heaps that we referred to as extra heap conditions. Absolutely none of that applies here, so forget it. I said we weren't going to talk about heaps anymore. Well, I'm only bringing it up to say that we don't have to worry about those complications that we had in heaps. Okay? Binary search trees are pretty much as described up to this point, organized as nodes with pointers, and we have left child, we have right child, and we have rules concerning the ordering of the data, okay, that we just discussed. And that's it. That's all that's required. Okay, so in particular, a node might have, a left child and a right child, or it might have only a left child, or it might have only a right child. Okay, unlike with heaps, it's possible for a node to have a right child but not have a left child. That's absolutely permitted here with binary search trees. Okay, and of course a node might have no child nodes. So hopefully that's resonating with you just as I described it above, but no doubt some simple examples will help to reinforce the idea, solidify it in your head. Hopefully this next slide will do that. Rather than thinking about complex data like student records, let's stick to something. Let's assume we're maintaining a binary search tree of integer values, right? And so these integer values serve as the key attribute. It's the only data in each node, okay? So here's the picture I have in mind. The yellow boxes represent nodes in a binary search tree, okay? The green box here labeled the BST, it represents an object that itself represents the entire binary search tree. Okay, if you think back to when we talked about linked lists, I did something similar. I had an object that represented the entire linked list, and then the linked list was made up of little structures, little nodes. Okay? Here, a similar thing. We have this object, dBST. It has a pointer that points to the root node of this binary search tree. Let me remind you again what that means, that every binary search tree has a node that is the starting point. It's at the top in this diagram, okay? And that's said to be the root node. Okay, so forget about the green object. That's not really important right now. Let's look at the binary search tree consisting of these yellow nodes. Okay, each one holds a data value, and each one has a left pointer as well as a right pointer. In some cases, those pointers point to other nodes, but sometimes those pointers are null. Okay? Well, as we see, the data stored in the root node is the number 5. And we also see that the root node has a left child whose data is the number 3, and it has a right child whose data is the number 8. Okay? The node whose data is the number 3, it has a left child whose data is the number 2, but it does not have a right child. Okay? And of course, the node whose data is 2 doesn't have any child nodes. Both of its pointers are null. It has no child nodes. It is, if you recall, said to be a leaf. A leaf is a node that doesn't have any child nodes. Okay, so that's the end of the road in that direction. But now going back to the node whose data is 8, we see that it has a left child whose data is 6, and it has a right child whose data is 9, and we see that both of those nodes are leaves. They do not have any descendants. They don't have any child nodes. Okay. So now it's time to pause and really carefully, very carefully check the ordering condition and make sure that we see that it applies here, that it's in force here. Okay, so let's start with the root node again, which has data value 5 together with its left child, which has data 3. Yeah? Well, certainly 3 comes before 5. So things are good over here. The left child has a value that comes before the parent. Okay, and that's as it should be. And in fact, all of the left descendants of the root have values that come before the root's value. Let's think about that. The root again is this node whose value is 5. Which of the nodes are its left descendants? Well, the answer I think is hopefully clear to you. Includes the nodes whose values are 3 and 2. Okay, the nodes whose values are 3 and 2 are left descendants of the root node, and of course the numbers 3 and 2 both come before the number 5. So that checks out nicely, right? And similarly, if we look at the right descendants of the root, well, those are the other nodes. Those are the nodes whose values are 8, 6, and 9. Okay? Each of those nodes has a value that is greater than the value of the root, right? 8, 6, and 9, they all come after 5. Okay? And if you check out all of the details, you see, there's not too many things to check here in this example, but for example, the node 8 has a left child whose value is 6, and it has a right child whose value is 9, right? And things check out there because 6 comes before 8 and because 8 becomes before 9. You probably anticipated this already, and I didn't write it in here as a bullet or anything, so let me just say it. Should have inserted a bullet here. Suppose we were looking for the number 6 in the binary search tree on the previous slide. Well, how would we proceed? Okay. You probably already figured this out based on your understanding of binary search and so forth. If you're looking for the number 6, you'd start at the root node and you'd observe that its value is 5. Well, since that's not what you're looking for, you then have to explore, should you go off to the left or should you go off to the right? And I think the answer is very clear at this point. The root has value 5. What we're looking for has value 6. So the node we're looking for would have to be a right descendant, right? So from the root, we'd go off to the right child and would come to a node whose value is 8, okay? And of course, 8 is bigger than 6. 8 is too big. So we would look at its left child, okay? And its left child happens to have value 6, so we found what we were looking for. Okay, we started at the root, whose value was 5. That was too small. Went off to the right, found a node whose value is 8. That's too big. Went down to the left, and lo and behold, we found a node whose value is 6, which is what we're looking for. Okay? What if we had been looking for the number 7 instead? Well, we'd proceed pretty much the same. We'd start at the root. 5 is too small. Go to the right. We'd find 8. That's too big. Go to the left and find 6. That's too small. So we'd want to go to the right child of the node whose value is 6, but that node does not have a right child, right? So at that point, we could conclude the number 7 is not stored in the binary search tree. I hope that makes sense to you. If necessary, go back and look at the example again. Okay, well, we've discussed this idea already. The green object in the green box in the previous slide basically is a visualization of an object that represents the entire binary search tree. Yeah, and that's a useful thing to do. It's not a universal practice in coding, but it's desirable to have an object that represents the entire binary search tree. Okay, well, what kind of data needs to be stored inside that object? Well, I would assert that at a minimum, it needs to contain a pointer that points to the root node of the binary search tree, right? Exactly what I have in that slide. The object that represents the whole binary search tree has a pointer that points to the root node. Okay. And then you could also put additional information into the object. For example, you keep track of how many nodes there are, and a couple other things come to mind, but they're not really essential, not in the way that this is. As long as that object that represents the whole binary search tree has a pointer to the root, that's going to be enough to let you get to the root node, and then from there you can navigate, you can follow the other pointers to navigate your way through the entire binary search tree. Okay? Well, we've already discussed, obviously each binary search tree node has a left child pointer that would be null if it doesn't have a left child, and similarly it has a right child pointer that would be null if it has no right pointer. We come now to an issue that's a little bit unpleasant. As nice as binary search trees are, and I say again, they really are quite nice because they tend to let you do they tend to let you do data lookups in logarithmic time and data insertions also in logarithmic time. But this doesn't always work out, and we're going to see an example now of how things can go wrong. Okay, so let's first remember the example that we just looked at. In the previous example, we had a binary search tree that stored the numbers 2, 3, 5, 6, 8, and 9. Okay, and as you recall, node had the value 5. So you can imagine that the number 5 was inserted first. Okay, the root node was inserted and it had value 5, and after that these other values were inserted. Okay? Question: is it possible to have a different binary search tree that stores exactly the same data, 2, 3, 5, 6, 8, and 9? And the answer is certainly yes. There are lots of different binary search trees you can hook up that all store exactly the same data, right? And in fact, there are some that are really not very nice, that are bad from the standpoint of our design goal, if you like, of having logarithmic lookup and logarithmic insertion. Because here's what could happen. Suppose instead of inserting 5 first, suppose these numbers were inserted into the binary search tree in exactly, their natural order, 2, 3, 5, 6, 8, and 9. Okay? So what would happen? We'd begin by inserting the number 2. All right, so the root node would be built, and its value would be 2. Okay? Then, when you went and inserted 3, there'd be a little search starting at the root. 3 would be compared to 2, and it would be realized that 3 should be a right descendant of the root. And since there is not yet a right child of the root, well, then a new node would be built right there. Okay? Root node would now have a right child node, and its value would be 3. Okay? Now, now when we insert 5, we start at the root and compare 5 to 2, and 2 is less than 5, so we'd look at the right child whose value is 3, and 3 is less than 5, so we would try to look at the right child of that node, but there is no right child. So it would be realized that the number 5 has not yet been inserted, and it would now be inserted as the right child of the node whose value is 3. Okay? And this continues. 6 would be inserted next, and it would wind up becoming the right child of the node whose value is 5, and then they would be inserting a node whose value is 8 as the right child of the node whose value is 6, and finally a node would be inserted whose value is 9, and that would be the right child of the node whose value is 8. And I think you probably anticipated this. That's a bad situation. Okay, we have repeatedly just inserted on the right side. We've only used right node pointers. We didn't use left node pointers at all. So we end up with this situation. We end up with the following binary search tree. Okay, so quickly check that that's a valid binary search tree. It's technically okay. The root is 2. It has a right child that's 3. Its right child is 5. The right child from there is 6. The right child from there is 8. The right child from there is 9. And that has no child nodes. Yeah, and there are no left child nodes, right? So what have you got here? You got a binary search tree, but it's effectively just a linked list, right? The left child pointers aren't being used at all. Okay, so what's going to happen if you try to search for something in this binary search tree? Well, you're basically searching a linked list. So pretend you go searching for the number 7. Well, you'd start, you could take advantage of the fact that it is ordered, but you'd start at 2. You don't see 7, so you go to 3, that's not 7. You go to 5, that's not 7. You go to 6, that's not 7. You'd go to 8, and you'd realize that 8 is too big. You'd try to look for a left child of 8, but there is no left child of 8. Okay, so you went looking for 7. You had to go all the way from 2 to 3 to 5 to 6, and finally to 8, until you discovered the fact there is no node with 7. Okay? Or let's say you were looking for 9. Okay, if you were looking for 9, you'd start at 2, then go to 3, then go to 5, then go to 6, then go to 8, then go to 9. You finally found it. But how long did it take you? It took you linear time, right? It took you, you're basically doing a sequential search, and you basically wound up looking at all the nodes. So it's taking linear time, not logarithmic time. Okay? We say that this binary search tree here is highly unbalanced. Okay? A nice binary search tree is more like the one we looked at the first example. A balanced binary search tree basically uses left child and right child in equal proportions, and it doesn't go down to a depth deeper than is necessary. Okay? If we think of this tree here, it has a root node, and then at the next level, there's one node. At the level underneath that, there's one node. Then there's one node at the next level, one node at the next level, one node at the next level. So there's 1, 2, 3, 4, 5, 6 different levels to this binary search tree, whereas the one we had previously, I think, only had 3 levels, right? It had a root node. That root had child nodes, and maybe some of those child nodes had child nodes, and that was it. Okay? Yeah. So the previous example was said to be balanced. This one is unbalanced. It should be very clear to you that balanced is much better, much more desirable than unbalanced, because when the binary search tree is balanced, you can do a nice binary search through it. You can do something that's going to take that's going to take only logarithmic time. Okay? The previous example could be searched in logarithmic time, whereas this one requires linear time. Okay, all of these things we've said already. Yeah, step through this at your own pace, and just check this out. This is pretty much what we've already said. So we like balanced binary search trees, and we don't like unbalanced binary search trees. Well, notice how we wound up building an unbalanced binary search tree. We did that by inserting the data in its natural order, right? 2, then 3, then 5, I forget the other numbers, and so forth. Yeah? If you want to maintain balance, it's best to insert randomly so as to avoid inserting things in the natural order. Okay, the natural order tends to linearize things and create an imbalance, whereas inserting in a random way, on average, tends to lead to a balanced binary search tree. Okay? But there's no guarantees. So it's worthwhile talking about the possibility that you end up in the unfortunate situation of having an unbalanced tree. And what you'd like to do something to sort of tweak it a little bit and end up with an equivalent tree, a tree that contains the same data, but which is more balanced than the one you started with. Okay? And in this regard, there are a couple basic operations that can be performed on nodes that are quite useful, and with a little bit of judicious application and planning, these simple operations can be used in combination to help balance an unbalanced tree. Okay? We're going to discuss these operations, which are known as rotations, in the second part, in part B of this lecture.